All right, so binomial settings. If we know something's binomial, then we can use the binomial distribution and the binomial formula. So first you have to know how to check if something is binomial. But the definition for this, binomial setting arises when we perform several independent trials of the same chance process and record the number of times that a particular outcome occurs. And more importantly, these are the things that you need to check for if it's binomial. And the shortcut is BINS to help you remember. Check your BINS, which stands for binary independent number and success. So, what does this mean? Binary means you have a success and a failure. So if you're flipping a coin, you can define heads as success and tails as failure, but there can only be two outcomes, all right? So if you were doing a dice, it would only be binary if you were saying odds and evens or something like that. Make sense? All right. Independent, you guys know what independent means, right? The first draw or the first trial does not affect the next trial, right? That's the definition of independent. If you know the outcome of the first, it does not affect the outcome of the next one. So something that would not be independent would be drawing cards and not replacing them, right? If you are replacing them, then they're independent. Number means you have a fixed number of trials. So maybe I'm going to roll my dice 10 times, or I'm going to flip my coin 50 times. But the problem has to state exactly a fixed number, okay? And then the success stands for the actual probability of success stays the same every time. So if you're flipping a coin, it's like a 50% chance every single time. If the probability changes, then it's not a binomial setting, okay? All right. Here are 3 scenarios involving chance behavior. In each case, determine whether or not the given random variable has a binomial distribution. Justify your answer. So, for A, genetics says that children receive genes from each of their parents independently. Each child of a particular set of parents has probability 0.25 of having type O blood. Suppose these parents have 5 children. Let X be the number of children with type O blood. So, basically, is it binary? And we're going to check our BINS every time. Okay? Now, you can't just do the shortcut on the AP exam because they don't know what BINS means. It's just to help you remember. So you actually need to say, like, is it binary? So, is it a yes or no answer here? What do you think? Yeah, I would say it's binary because you're either type O blood or you're not. That's how they're defining this. Okay. And independent. How about independent? Yeah, it says it. That's nice. Okay, it gets each of their genes independently. The outcome of the first child doesn't affect the outcome of the next child. Okay. And then we've got N. What's N stand for? Yep, your fixed number of trials. What is that N number in this problem? Yes, they had 5 children. All right, what's the S stand for? Success. Good. And is that probability of success the same every time, and what is it? Yep, it's a 0.25 chance every single time they have a kid that they're going to have a kid with type O blood. All right? So, is this binary? Yes, binomial. Thank you. All right. Shuffle a deck of cards for the next one. Turn over the first 10 cards, one at a time. Let Y equal the number of aces that you observe. So, did they replace the cards, you guys? No. So is it binomial? No. Okay, so we could check everything, but if we already know 1 is not true, it's not independent, and so it's not binomial. All right, shuffle a deck of cards. Turn over the top card. Put the card back in the deck and shuffle again. Repeat this process until you get an ace. Let W equal the number of cards required. So is it binary? Yeah, you're either getting an ace or you're not. Are the trials independent? Yep, you're replacing the cards. Is there a fixed number of trials? No. All right. So since there's not, nope, because n is, we don't know. All right. They have to say I'm going to draw it a certain number of times. Okay. You guys got that? Do you want to do another one? No? All right. Inheriting blood type. Calculating binomial probabilities. So now we're going to actually calculate them. First you have to check, is it binomial? Then we have to know how to calculate them. So each child of a particular set of parents has a probability of 0.25 of having type O blood. Genetics says that children receive genes from each of their parents independently. If these parents have 5 children, the count X of children with type O blood is a binomial random variable. Where n is 5 trials, the P is 0.25 of success in each setting. And a child with type O blood is considered a success, and a child with another type of blood is considered a failure. What is P of X equals 0? So, what's the probability that none of the 5 children has type O blood? It's the chance that all 5 don't have type O blood, right? That's always the probability of 1 minus none. Complement rule. All right. So, by the multiplication rule for independent events, if I have none of them, so everybody's a failure here, not type O blood, so the probability of getting O blood is 25%, so the probability of not getting O blood is 75%, and it has to happen 5 times in a row, right, for all 5 children, which gives us this lovely 24-ish% chance, okay? So that'd be none of them get it. How about 1 kid gets it? All right, just 1 kid. Well, there's a few combinations, right, of this. I could have the first kid is a success, and the other 4 are failures. In that case, the first probability is 0.25, and the other 4 are 0.75, right? And then we figure out that probability. But what other combination could I have? The second kid could be the success, or what else? Yeah, it could be the third kid who's a success. In that case, what would we multiply? 0.75 times 0.75 times 0.25 times 0.75 times 0.75, right? And we could move it to the next person in line. 4th person and 5th person. And we could calculate all of our lovely probabilities. Are they all the same anyways? Every single one of those? Yeah. You can multiply in any order, right? So we're going to get that same 24% every single time. However, we've got all the different combinations that we have to account for. And how many combinations are there? 1, 2, 3, 4, and I didn't do the last one, right? 5 different combinations. So we actually have 5 times 0.25, which always wow, that's special. 0.25, which always happens 1 time, right? So that's to the first power. And 0.75, which always happens 4 times. So we have 1 success and 4 failures. And we have 5 combinations of that, which gives us our final answer of 0.3955. So about a 40% chance we're going to get 1 kid with type O blood. All right? That's exactly 1 kid. So let's continue with the scenario from the previous example. What if we want to find the probability that 2 kids have type O blood? Exactly 2 kids. Well, let's see. Probability that x equals 2. So that's the probability that we could have our first 2 kids be successes and our last 3 be failures, right? And so for successes, what are our probabilities going to be? 0.25 to what power? Okay. And 0.75 to what power? 3. And we have to think of every combination of 2 S's and 3 F's, right? There is always, this is always going to be the formula then. It's going to be the number of arrangements times the probability of success to the k power times 1 minus the probability, which is our failure, to the n minus k power. What does it stand for? P is our probability of success. Okay, this represents the probability of failure, 1 minus P. K is the number of successes we want. N is our number of trials. So for this, we had like 5 kids, and we'd subtract 2, okay? So N is trials, and subtract K. I just did that. All right, so the shortcut for just the number of arrangements, okay? Instead of like going through and actually having to like write out all the different orders of the successes and failures, we can shortcut it. It's called the Binomial Coefficient, and the formula that you might remember, this is actually NCR on our calculator. They write it, actually K, sorry, but R is what our calculator uses, so I'm going to leave that there. But K and R are the same in this, all right? So they use parentheses like that, the N over K. You want to be able to recognize what that means. It's just combinations. We actually never really use this, but you've probably seen it before, so I wanted to show you where it comes from. You can totally just use your calculator for this. So in the last problem, for our NCR, we would do 5 trials, choose 2 successes. So you guys, on your calculators, find where this is. So go to TI Inspire, menu, probability, combinations. Or if you have the 84, go to probability, math, probability, NCR. And plug it in, and let's see how many combinations we have when we start with 5 kids and we're choosing 2 to be successes. If you don't have a calculator, I would write this formula down so you can see it. This is how it's typically going to look on your formula sheet. Probability that x equals k, where k is whatever you determine as your number of successes. X is your random variable, you guys. It's whatever you define as. Like in the last problem, it was getting type O blood. N is your trials. Sometimes the answer won't be there. It'll just be in the formula form like this. So you just want to pick out the correct formula. P is probability of success. That next part's probability of failure. K is the number of successes you want to get. Okay, so let's try one. Each child of a particular set of parents, same probability, type O blood, same 5 children. Okay, find the probability exactly 3 children have type O blood. So part A, probability that x equals 3. So in our parentheses here, because this is how they're typically going to write it, we're going to do 5, choose 3, which we can plug into our calculator with NCR, okay? And then what number goes next in the formula? Okay, and what exponent do we want here? We want 3 successes. And what probability goes next? Yep, and how many failures do we want? Yeah, these always have to add to our total number of trials. Okay, plug that into your calculator. Try it. Do the NCR. Plug that whole thing in. Tell me what you get. All right, so we get 0.0879-ish. Okay? No? So then always answer the question, you guys. There's about a 9% chance that exactly 3 children out of your 5 children will have type O blood. All right? Now, the part B is where this gets really fun. Should the parents be surprised if more than 3 of their children have type O blood? So now we have to do the probability of more than 3. And you should probably write this one down if you didn't take notes. All right. So more than 3 children. Well, what does that mean? How many children is that? Yeah, that really means exactly 4, or, which is addition, exactly 5. How many times are we doing this formula? Twice, and adding it together. Sometimes it's way more than that, all right? So this one was actually not too terrible. So for this first one, it's going to be 5 choose 4. Okay, out of my 5 kids, what if exactly 4 of them are type O blood? What's the first probability? 0.25. And we want 4 of them exactly to be a success. And we want 1 of them to be a failure. Plus. Next one would be actually 5 choose 5. What if all 5 children are type O blood? Seems unlikely, but for this one, you guys are going to do 0.25 to the 5th and 0.75, what do you guys think? Yes, to the 0. None of the kids will have type O blood. Okay, you can plug them in separately or possibly together. You can probably put that whole thing in, but it's 0.015-ish plus 0.0098. Oh, wait, one more 0 in there. 0.00098. And add them together, we get 0.0156. So there's like a 1.5% chance that 4 or 5 of your kids, or more than 3, will have type O blood. Alrighty, so you do need to know the formula, but of course there's shortcuts. Statistics. Everything is easy on your calculator. So we have an even better way of doing these on your calculator. You need to show me both on the worksheet today with the formula, because you have to be able to recognize the formula on the test. But eventually you can start doing a lot of this on your calculator. So distributions, if you guys remember where that is, you go menu, probability, distributions. There are 2 binomials. They're pretty far down after you go to distributions. You have to scroll down. There's binomial PDF and binomial CDF. All right? So PDF is for exactly 1 outcome. Like, I want exactly 2 kids to have type O blood. So like the problem part A, okay? And then there's the binomial CDF. I always think of C as like cumulative, kind of. So that means you have a range. So this is where if I want to have more than 3 children, my range goes in there. So let's try the exact same problems, A and B, but on our calculators. All right. So for part A, I need a different color pen. We're going to do binomial what? PDF, okay? And what do they ask us to plug in on this? Okay, the first thing is number of trials, so they give you an N, right? How many trials do we have? 5. What's the next thing they give you? So they give you P. Probability of success is what? 0.25. That's what we're going to plug in for P. And what's the next thing they ask you to plug in? The X value. So that's the exact number of successes that I want. We're going to put a 3 in. And hopefully you get a very similar answer. Okay, they're not always exactly the same just by calculations, but this should be pretty close. All right, let's try the cumulative one. So on this one, we've got binomial CDF. Okay, and this has some different things to plug in than the last one. So it asks for number of trials. We're going to put 5 for n. Probability of success, 0.25. And this time we have a lower bound and an upper bound. For this one, what do you guys think our lower bound is? It is 4. All right, don't do 3. We want to be inclusive, so it's 4 or 5, so it's from 4 to 5 on this guy. By the way, this is the same thing when I write this probability as x is greater than or equal to 4, just so you know. Greater than 3 is the same thing as that. All right, so those are our calculator functions. Just remember that you have to state what you used and what these are. You will not get full credit for this on the AP exam. You have to use this. So be specific. Trials, P, X value. That's pretty easy. All right. All right, so let's try these on our calculator and see if we can get it. All right, a local fast food restaurant is running a draw 3, get it free lunch promotion. After each customer orders, a touchscreen display shows the message, press here to win a free lunch. A computer program simulates one card being drawn from a standard deck. So we're using a deck of cards. If the chosen card is a 3, the customer's order is free. Otherwise, the customer must pay the bill. So, part A. All 12 players on a school's basketball team place individual orders at the restaurant. What's the probability exactly 2 of them win a free lunch? So we'll do this one with our calculators. So is it binomial PDF or CDF? It's exactly 2, so PDF. All right, and the first thing we plug in is our trials. How many trials are there in this particular problem? Yep, 12 players. And our probability of success. Well, read this part, right? We're looking for a card of 3. How many 3s are in a deck of cards? So you can actually just put 4 over 52. And then our X value is what? We want exactly 2 winners. And you guys get 0.1754? Awesome. All right, and part C, if 250 customers place lunch orders on the first day of the promotion, what's the probability that fewer than 10 win a free lunch? Fewer than 10. So binomial, by the way, I probably should be saying this, probability that x equals 2. And for this one, I should be saying probability that x is less than 10, okay? So anyways, binomial PDF or CDF? Yep. So binomial CDF. And what's our number of trials for this problem? What? 250. This is a different problem than part A, right? Our probability of success does stay the same. We're still saying the 3s out of the deck of cards, right? And now we have our lower bound and our upper bound. What's our lower bound in this one? It is 0. Yes, you could have none of those. Okay, and what's our upper bound? It is 9. Very good. Less than 10. So you got to go only up to 9. Plug that in, and you should get 0.006. So pretty small chance there.